Let's get started. So we're going to most likely finish up chapter 16 today, and then we'll start chapter 17. I might hint at chapter 17 at the end of the lecture. We see how far we go. So at the end of lecture on Monday, I talked about the Wittig reaction for the last 2 or 3 minutes. And so the Wittig reaction stays within the theme of chapter 16. The theme of chapter 16 is the addition of nucleophiles adding into carbonyls. Particularly only 2 types of carbonyls, aldehydes and ketones. So chapter 16 is nucleophiles into aldehydes and ketones part 2, because that's what chapter 12 was as well. So in the Wittig reaction, we take what we call a phosphorus ylide, and I'll talk more about phosphorus ylide shortly. But we take a phosphorus ylide, which is a carbon with a minus charge, bound to a phosphorus with a positive charge. So phosphorus likes to have 3 or 5 substituents. If phosphorus has 3 or 5 substituents, it's neutral. If phosphorus has 4 substituents, it's going to have a positive charge. And this is something that should have been covered in Chem 200 and 201. Just like aluminum likes to have 3 substituents to be neutral, and if it has 4 substituents, it has a minus charge. Again, this is all the Vesper theory and the stuff that should be covered in Chem 200 and Chem 201. I know it's covered in Chem 200 or 201, but I guess people don't really appreciate the organic ramifications of those concepts when they're taught in Chem 200 and Chem 201. So when phosphorus with 4 substituents can have a positive charge, and of course carbon like this can have a minus charge. And we have a carbonyl, and you can guess if you have a carbon with a minus charge, even though the minus charge is stabilized by the phosphorus with a positive charge adjacent to it, it's still a carbon with a minus charge, so it's going to be fairly nucleophilic. So unsurprisingly, the carbon with a minus charge and the phosphorus ylide, Y-L-I-D-E, and again, the ylide is just a molecule that has both a positive and a minus charge. So the ylide is going to attack the carbonyl, just like you'd expect the carbon with a minus charge to attack the carbonyl. And you get this intermediate shown here. And now, 3 bonds from each other. We have an oxygen with a minus charge, so this bond going up to the oxygen, and we have a phosphorus with a positive charge. What's going to happen? Well, the oxygen with the minus charge can give 2 of its electrons to the phosphorus with a positive charge, and that's going to give us a neutral molecule, which is this 4-membered ring. This 4-membered ring with the phosphorus bound to an oxygen, and then the 2 carbons from the aldehyde and the carbon from the ylide bound to each other. And then once we form this, 2 things can happen. Right, the first thing that could happen is these electrons could go back into here to give us this, and then maybe this could fall apart to give us this. Again, macroscopic reversibility. In this class, I think if we've learned anything, we've learned that any chemical reaction, if there's enough energy in the system, can be reversible. That doesn't mean they are reversible. It means if a bond can be formed, a bond can be broken. Just realize sometimes breaking the bond may cost more energy and will be tougher. So we can definitely go backwards, and that's a possibility. Or from here, we can go forwards. And the question is, how can we go forward? And the way we can go forward is by what I referred to on Monday as square dancing, where these electrons from this oxygen carbon bond that was originally in the carbonyl in green can jump up here. And then these bonds with between the phosphorus and the carbon in the ylide, as a response, can go there. So this error pushing happens at the same time. There's no correct order of how the electron pushing happens. It just happens concertedly. And what that gives us out is a substituted alkene, which is the product we care about. The product we care about is the alkene. And also we get out triphenylphosphine oxide. And so the driving force of this reaction is the stability of triphenylphosphine oxide. Triphenylphosphine oxide is a very stable intermediate. The phosphorus-oxygen bond is highly stabilized. And the reason the phosphorus-oxygen bond is highly stabilized is because, frankly, so the phosphorus is lower in the periodic table, right? So the phosphorus has d orbitals. So the reason why triphenylphosphine oxide is so stable and these are just phenyl groups I'm doing in shorthand, is that the lone pair of electrons on the oxygen can partially delocalize into whatever d orbitals we have. And that gives us electron delocalization and that gives us stabilization. Don't worry about that. I just felt like I needed to explain why phosphine oxides are so stable. And it's because of the d orbitals and the phosphorus cause for more electron delocalization and more stability. So because phosphine oxides are so darn stable, this really drives the reaction forward. So the reaction is driven forward by the fact that we're giving off a stable product plus an alkene. So what does that mean? Well, that means if you have an aldehyde and a ketone, we can add a phosphorus halide and make a double bond, a carbon-carbon double bond, where two of the substituents are from the aldehyde and the same are ketone from the same carbon, and the other two substituents are from the phosphorus. So in other words, these two things are swapping partners with these two things. So they do their square dancing and then they switch partners. I believe is that do-si-do? Does anyone know what the proper nomenclature for square dancing is? I don't. What?
I think it's 2 steps.
So when they switch partners?
Switch your partner round and round.
Yeah. So this is the round and round, grab your partner round and round, and then it's stopped. Then you switch partners, and then it stops. No one knows. I have no idea. I've never gotten any type of square dancing in my life, which is my gift to society. I promise you. So once again, we're forming a double bond where the aldehyde swaps its oxygen for the substitution on the ylide. Just to give you a quick example of what I mean, let's take acetone. And let's take this benzyl phosphorylate. All right, and then the product we will get out will be this plus triphenylphosphine oxide. So once again, the acetone, it's wiping its oxygen for this substitution. And then of course we'll have triphenylphosphine oxide, which is the partial driving force. So once again, the Wittig is a good way to make double bonds. And it goes through attack of the phosphorus ylide into the carbonyl, and then switching the partners in this conservative fashion where one bond goes up and the other bond goes down. Give us our double bond. I'll show you more examples, don't worry. I just want to talk about some other things first, along the lines with the ylide. So, you notice how so far I have only used ketones that are symmetrical. Now by symmetrical ketone, I mean the substitution of the carbonyl is the same. And so that means then these, the resulting double bond doesn't have cis or trans. Because there's a plane of symmetry, right, among this group, so there's no cis and trans because it's methyl and methyl. But, let's say we switch it out. Let's go benzaldehyde. So an aldehyde off of a benzene ring. And let's do that same benzyl phosphorus ylide we just mentioned about. By the way, these circles with crosses with them, they're shorthand for phenols. So if I draw a circle with a cross in it, so a psi, that's a phenyl group, that's a pH. So that's a phenyl group. So of course we have a minus charge here. So by using this stuff, we can get two products out. Apparently I'm colorblind. So the two products we can get out are, well first, let me draw the two possible four-membered rings. So we can have it where it forms so the phenyl groups are on the same side. Or plus or we can have it so now the phenyl groups are trans to each other. So just for fun. So when we do the final step to give us our triphenylphosphine oxide and our product, will this phenyl group cis to each other in a ring, will this give us the cis or trans olefin? It'll give us the cis olefin, absolutely. Alright, and so now when we have the four-membered ring where the phenyl groups are trans to each other, will this give us a cis and a trans olefin? It will give us a trans olefin, of course. Very nice. So my question to you is, which one of these do you think is going to be more thermodynamically stable? Or more specifically, let me say, which one of these transition states, which one of these intermediates do you think is going to be more thermodynamically stable? Yeah, this is going to be more stable, so you would expect this to be a kinetic product. So indeed, trans is the kinetic product. So if I'm calling this a kinetic product, am I showing my cards about this? Yeah, the cis is actually the, so sorry, to erase everything, let me do the Wayne's World stuff. The Scooby, I guess it's really the Scooby-Doo rewind. So, the trans is the thermodynamic product. No big surprise. So this is a thermodynamic. If I'm calling this a thermodynamic, that means I'm implying this is the kinetic. And that is the case. Now I'll explain why in a second. But just for now, cis is kinetic, and trans is thermodynamic. So why is cis kinetic when this intermediate looks like it's so much higher energy than this? Because we have this nice steric clash. Well, that must mean that the transition state of this attacking this must be lower in energy when it gives us a cis product. And that's true. And so let me show you, let me explain. Let me make sure I stick to my green and orange nomenclature so everything is hard to see, easier to see. All right.